Hello, I'm Hyunsu Kim. Today, I will present a solution for resolving a problem when using Markov chain Monte Carlo for variational autoencoder. This solution was invented together with Ju Lee and Hongsuk Yang. Our goal is training a discrete variational autoencoder. The target model consists of the generative model P with parameter theta and the inference model Q with parameter phi. X is the data variable, and H is the latent variable. To train this model, we maximize the marginal log likelihood, log P of X, and minimize the KL divergence between P of H given X and Q of H given X. In order to accomplish this, we aim to calculate the gradients of both objectives for the stochastic gradient descent. Since the direct calculation is infeasible, we have to transform the gradients in terms of expectations over P over H given X for Monte Carlo estimation. The weighted wake sleep algorithm was the first to utilize the importance sampling for an estimation. Note that it uses the variational distribution Q as a proposal distribution. More recently, joint stochastic approximation, aka JSA, runs Markov chain Monte Carlo for this estimation. Note that the MCMC also uses Q of H given X as a proposal distribution. Since the sampling is still parallelizable, we can exploit the low variance of MCMC with a little more computational time. This leads to better performance than reweighted wake sleep. However, we discovered a problem with JSA performance. It highly depends on the initial samples of the Markov chain. There are two candidates for initial samples. The first sample consists of new samples from the proposal distribution Q. The second sample is reusing samples generated from the last epoch. We can refer to the first sample as interns and the second samples as retirees. As you can see in the figure, the key point is that the target distribution P and the proposal distribution Q both keep changing during training. We call this the non-stationary kernel problem. With this in mind, if we use the intern samples as initial samples which came from the current Q, then the next MCMC samples easily track the changing targets and the proposals. If we use the retiree samples as initial samples, it must be closer to the target than the interns. However, the next MCMC samples may not easily follow the changing distributions, especially in the early stage of training where it changes a lot. This means the intern samples show high effective sample size but low accuracy, whereas the retiree samples show high accuracy but low effective sample size. We observe this claim by running JSA in different settings. Each line in the figure represents change of negative log likelihood. The blue line shows when we only use the intern samples. The other lines begin with intern samples, then switch to the retiree samples at various points. At the orange line in the figure, you can see the line immediately drops after switching, and then it slowly diverges. This phenomena comes from low effective sample size. Our solution centers around tracking the acceptance probability of MCMC. Low acceptance probability causes many duplicate samples, so the effective sample size gets very low. The algorithm should measure this probability. If it is significantly less than 1, we should use the intern samples. Otherwise, we should use the retiree samples. The resetting chain phrase indicates the initialization of the chain using the intern samples which don't come from MCMC. You can find more detailed information in our paper on openreview.net by searching the keywords AABI 2021 non-stationary kernel. Thank you.